Okay, next presentation is going to be made by Leire Segura. She is the responsible of electrical generation activities in electrical systems domain in Airbus company, and the presentation is going to be about the more electric aircraft.
Okay, so good morning to everybody, and thanks Mr. Chairman, and thanks to the organizer for this invitation. My objective is to give you a general view, a very general view, on the more electrical aircraft concept. That is one of the key concepts of future aircraft. So, as I'm saying, it's going to be very general, but do not hesitate if you have any questions on the concepts or on the equipment we are going to talk about, to ask whatever the questions you may have. I will try to answer them as better as possible. Okay, so regarding the first part, the introduction, Jan has already done a nice introduction on the concept. What do we want with the more electrical aircraft? Let's say we are thinking on equipment that are lighter, smaller, more performant, more beautiful if we can. Okay. Let's say that this is a trend that is not really new. Let's say that it's the trend that has existed since the beginning of the aviation. You can see that at the very beginnings we had no electrical systems, no electrification in aircrafts. We had no electrical systems in general industry, so aviation was just another example. With the pass of the years, as electrical systems have been developed for other industries, they have also been implemented in aviation and in aeronautics. So let's say that in our case, already in 1980s, we had aircraft that had installed electrical power of around 200, 250 kilowatts. In the next decade, in 1990s, we increased the installed power to 500 kilowatts more or less, due to the existence of new electrical systems and the possibility to implement them, taking into account the aeronautical limitations and norms. And finally, in last decade, with the A380 aircraft development, that is the biggest civil aircraft of passengers we have developed, we have reached installed electrical power of above 800 kilowatts. So this is just to give you some figures on the installed power that we have in current aircraft, and to see that the more electrical aircraft trend was existing, is supposed to continue. We want to continue. So let's say that if we can imagine the very end of the chart, it would be with 2 points. That would be the hybrid propulsion aircraft, and why not the full electrical aircraft? This is with full electrical propulsion. Okay, so let's say that that this is the trend. So let's have a look at where are we today. So in this chart, in this picture, I wanted to show you what are the repartition in terms of type of energy and type of power source in the aircraft. I guess you cannot see anything, so I will just give you the colors we have. All the things that you are seeing in blue are the pneumatic loads or supplying. For the hydraulics, you can see them in green, the electricals are in red, and the mechanical ones in gray. So, just without going into the detail, you can see that there is a large repartition in terms of type of loads. For the pneumatic loads on supplying, the main objectives or the main uses of this kind of energy are for air conditioning, for anti-ice system, and for engine and auxiliary power system starting. For the hydraulic parts, mainly the flight actuators. You can see the slats, the flaps, the trim, some spoilers. After that, there are some actuators that have become electrical or electro-hydraulical. This was mainly performed in the A380 aircraft when we start with the concept of fly-by-wire. So there are some that are being now developed by the electrical part that is also responsible for cockpit power supply and for the avionics system. And finally, we have very few loads that are driven now mechanically, that we can see in the engine drivetrain, for example. So let's say that what we can see here, even if you cannot see it, is that the type of loads is very different, and a kind of harmonization should be interesting for the future aircrafts. Okay, so this is linked to the reason to need or to use a more electrical aircraft. If we take the example of an A330, that is a long-range type of aircraft, was developed in the 90s, we see that we've got four power sources, four different power sources. This is the electrical, hydraulic, pneumatic, and mechanical ones, shown in the chart before, and three power networks. This is electrical, hydraulic, and pneumatic. So this means that a huge part of the efforts of energy transportation inside the aircraft are just to supply and bring to the loads three different types of energies. So this point brought us to think that rationalization could be a good trend, and instead of using four power sources different and three different power networks, our trend should be to try to give one power network and one power supply. So what are the opportunities that can bring us the use of one power network and only power supply, of type of power supply? If you can see in the left part that when we size the power sources for providing the energy to the loads, the rationale and the way of working we take is we take the worst case, we size the power source for that worst case, and afterwards we take some margin. Okay? And we do the same thing for each of the power sources we have. So finally, we find that we've got four power sources that are sized for the worst case, plus four margins for we don't know what the case can be, but just to be sure that we arrive to give the specifications needed in all the cases. If we go to a single power source approach, thanks to the mutualization, we are going to make the installed power smaller. Let's say that the quantity will be less, and the margins can be also reduced, because finally they are associated to the quantity of installed or really installed power. In addition, what we expect with this electrification is that instead of sizing the power source for the worst case, making a more intelligent distribution of the power, so that we can make the sizing for the average cases. Also having some margin just in case. But let's say that the approach is very different, not only by the quantity of type of power sources, but also because we don't want to be clearly oversized, as it's the case in all the aircraft we have currently flying. Okay, so that's the rationale, and here you have the challenges we are facing. In this chart, I am showing you what are the products we want to have in the aircraft and the concepts we want to have in the aircraft. So in terms of energy production, we've got the auxiliary power unit that will be used only for the electrical power supply. So there will be a simplification in this system. Regarding the electrical generation, this is one of the most important challenges. We must improve the technical part on them, because they are going to be the only and the main power producers of the aircraft. So we need to achieve some figures in terms of power, in terms of speed, in terms of integration that we haven't reached before. Finally, regarding the network, storage becomes one of the key points also. We are going to use reversible network. We can accept loads that are generating energy to the aircraft. For example, all the actuators that can supply, in some cases, power to the aircraft will be used for regenerating power. What should we do with that power? Usually we can feed other loads, but we also are going to put in place some systems that are able to store that energy, so that we can use it when we need it and not in the moment. Regarding the conversion and distribution part, there is a complete change of mindset. Let's say that currently the approach is to have a distribution center as the method and the concept to make power available for the consumers. Now what we want is to have an intelligent power center that is able to see what are the requirements and the demands of the loads, organize them, and give give each load the power that is required. This is one of the points that will allow us to implement the concept of generators size for average power and not for the worst case, because we will have an intelligent power center allowing this concept to exist. Okay. Afterwards, there will be the integration part that will be one of the key concepts also. There is the physical integration. Historically, we have had some problems when each of the systems have been developed in its corner. When we put all of them together, and we see that, for example, we have some problems in the, I don't know, in the wiring of the aircraft, as it happened in the A380, or in the integration of different parts of the aircraft. So let's say that the approach is completely different. And now we are trying to make a physical integration that is completed from the start. I mean, from zero, we are working clearly in this point. Regarding the functional integration, it's also a key point. This is now we are not supposing that power suppliers are in one side, power consumption in another side, and they are not correlated. It's linked with the intelligent power center concept I was mentioning. This is now if a load can regenerate power towards the aircraft, we will have to be able to integrate that load with that power system, with that storage system. So it will be more demanding regarding this point of integration. Finally, and just to finish with the power center, we've got a concept, it's high temperature electrical power center. It's just to remark that the cooling or the temperature operation of the power center will be one of the most interesting points. The discussion is, currently we have high efforts on cooling, on making the power electronics part able to operate in the rough conditions we've got in the aircraft. So let's say that there are some concepts that are on the table. One of them is the high temperature. Other concept and maybe other question is, can we make liquid cooling available for the whole modular power center? And the third question that we would like to answer yes is, are we able to produce a power electronic power center able to be cooled by air? This is with efficiencies that are above 99% maybe, but this is our objective. Okay. Finally, in terms of use, this is the loads. We are going to pass or to make some loads become electrical. So, for example, instead of bleed generation by the engine, we are going to have electrical packs. For the cooling, as I was saying, we are thinking on modular cooling, but when we are talking about modular cooling, we are meaning that the cooling of the power centers will be modular also. After that, there will be the part of the actuators. So the flight actuators currently are mainly hydraulical. We want to go clearly through electromechanical actuators. And finally, the eye systems. Let's say that there is also a change of the mindset. Currently, we've got two types of approach. We've got the de-ice approach, the anti-ice approach. So now the challenge is to make these systems electrically and able to perform the same operation that they are doing today. So it's in an anti-ice type of approach. Okay. So this is the objective we have. This is what would we like to have. Okay. So going a little bit into detail and linked with the works we are developing. Regarding the energy production, what are we talking about? What does it mean, more electrical aircraft in this part? So in a conventional aircraft, we've got the engine that is mainly used for the propulsion function, as you already know. But we take advantage of the existence of it to supply some other functions as electrical generation. The electrical generators are directly connected to the engine, bleed generation, hydraulic generation, and the engines are started by using bleed energy. Okay. In a more electrical aircraft, the engine will continue with the propulsion function. This is when we talk about a more electrical aircraft, we are excluding the engine part or the propulsion part as possible electrical. But for the rest of energy generation, we are only using it for electrical generation. As we are making disappear hydraulic and bleed generation, there will be no more in the engine. So that should make a simplification of the engine. Regarding the starting, as we have made disappear the bleed, the starting will be made electrically thanks to the electrical generators that are installed. If we go to the auxiliary power unit, let's say that this unit is made mainly for electrical generation and bleed generation. There is no propulsion function, and this power unit is started using also bleed power. There is a little mark there to say that this has been the trend in all the aircrafts, but in the A350, that is the aircraft that will enter into service in the next months, the starting has been already performed electrically. This is the starting system is fully electrical. Okay, so this will be also the trend for the more electrical aircraft. This is using electrical starting, and now it will only be used for electrical generation. So, for example, in the auxiliary power unit, when we forget about the bleed generation, we can think in an auxiliary power unit that is really more simple and lighter, and clearly lighter. So we can see some advantages in other associated systems from the fact of not having other types of energy. Okay. Regarding the electrical generation and distribution, okay, currently what are the type of equipment we have? For the high power equipment, the connection or the bus bar we are making available are 230 or 150 volts AC. We are making AC generation. What are the type of generators? In the first aircraft, they were fixed frequency generators, the so-called IDG, and from the last decade we are using variable frequency generators. Okay. So as I was saying, this kind of network is used for the most powerful loads. So let's say that all the loads must be supplied by AC power. In the more electrical aircraft, we are introducing a new concept, that is the DC generation possibility, and it's not that we are implementing pure DC electrical generators, but we believe that a distribution in a high voltage DC is a clear advantage for the loads, for the high power loads. So what we are doing is making implementing some new concepts on the generators so that they can generate at variable frequency, but we are not constraining the range. We are rectifying this output so that we can supply the DC bus bar. In addition, as I was saying in the previous slide, electrical starting is needed for the engine and for the APU, so there will be an electrical system to perform, to help to perform this kind of task. Okay, just to give you the figure, the network we are thinking about is 230 volt AC, and high voltage DC for us is plus minus 270 volt or 540 volt, as you prefer. Okay, regarding the low power loads, currently what we have is the 28 volt DC distribution part. So how do we achieve this power supply? The main supplier is the AC bus bar. So what we use is an AC-DC converter. Currently it's a non-controlled converter at TRU. And it's the main supplier, let's say converter, so, to provide this 28 volt DC power. We are also supported by batteries. Okay, they have been always used as a storage solution for cases where we have a reconfiguration, or we have some cases where the converter is not available. So they are used mainly to give some seconds of support and to support also some operations. In the current flying aircrafts, there are NiCad batteries. Currently we are switching to lithium-ion. In the A350, for example, as I was saying, in the next 2 years we expect to have lithium-ion batteries already flying. Regarding the DC generation or the DC distribution part for the low power loads, clearly what we are going to use are lithium-ion batteries. I mean, we don't expect to use NiCad in the next 20 years. But let's say that there will be new functions that will be done by this generation part. This is currently, as I was saying, we are only supporting some operations. The objective is to have a system that is able to help us in some hybridization operations. For example, for the emergency cases, we have a REM air turbine that is giving the, let's say, the essential energy for the essential loads, so that we can secure the aircraft arrival. What we believe is that with the technology we have today, we are able to decrease the size of that turbine, because now currently it's around 200 kilograms. So for a system that is only used once in the aircraft life, or even less, it's not a very good compromise. So for example, we are thinking on lithium batteries as the possibility to help us giving some of that emergency power. Why not, if technology allows us the full power, I mean the full emergency power, if the technology demonstrates that it's able to provide that quantity of energy during the 45 minutes, that is the worst case. But let's say that the trade is clearly to go to another technology in terms of batteries, and also to implement new functions on it. Finally, in the conversion part, in the current architectures, we have 150 volt to 20 volt DC AC-DC converters, AC-DC isolated converters, and also auto transformer units from 230 to 100 volt. Finally, we've got the static inverters. They are only used in severe case, let's say, when we want to supply AC power bar starting from batteries. Okay. Let's say that the conversion, as I was mentioning before, is one of the key points that is completely changed in this approach of more electrical aircraft. The principle we are going to apply is the principle of shared resource. What does this mean? Currently, what we do is providing power available for the loads. What do we want to do now is organizing the parts of the power center, so that each load can be supplied with the resources we want. Okay, so that's the reason to have modular power electronic blocks that will be configured or used for different loads. This is a function that currently is being done internally by the loads. They have their own power supply, so that they can adapt the energy they need to their own needs. And what we are going to have now is that instead of having small converters in every load, in every electrical load, we are going to centralize them in the power distribution center, and that will be the principle for avoiding that heavy part of all the loads, and to optimize and rationalize this point. Finally, we've got a DC-DC converter that is to be used mainly in emergency cases. It's a 10 kilowatt DC-DC converter. The topologies that are being promoted have been already presented. So let's say that this is one of the key challenges. This is developing a full converter able to fit in the aeronautical constraints, able to demonstrate the figure of safety that are needed in aeronautical and in emergency cases, and to demonstrate also that power conversion can be used and can be a real competitor for example, the hydraulic and pneumatical solutions we have today for the emergency part. Okay. So just to give you some pictures of what we have today, what will we have tomorrow. Let's say that this, as it's marked, it's a functional scheme. Okay, it's not really representative of what we have in current aircrafts, but we have the elements I have mentioned. Okay, you can see that we've got the engine, 2 generators per engine, or 1. It depends on the model, on the aircraft model. We've got the bus bar of 230 volt. We've got the bus bar of 115. The TRU that is providing us the 28 volt, and the batteries, and the loads that are being supplied by the 3 type of buses. Okay. Here you can see that the power conversion is very simple. I mean, we are only just to provide some simple solution. The power rating of, for example, this power electronics is around 10 kilowatt for the TRU, 10 for the static inverter, and I would say something like 40 for the ATU. So let's say that the most important part is only the generator plus the first bus bar. The rest is just to ensure that low power loads or low load consumers are well established. And now, what's the approach that we are proposing for tomorrow for the more electrical aircraft? Will be something like this. We can keep or not, to be decided, the 230 volt AC bus bar. We are creating a new HVDC bus bar, as I was saying, with the generator being rectified. The generators, they will have the starting function, so with the associated electrical system. And we have in the middle, as I was saying, the modular reconfigurable conversion center. This is a set of different converters of around 30, 45 kilowatts that will allow to make the power adaptation for all the loads that will be connected. This is mainly we can have loads connected to the HVDC bus bar, but most of them, we suppose them to be connected to the output of the power conversion center. Okay. Finally, we've got also the converter that will make the conversion between the power center and the battery, so that it can supply also the 28 volt DC loads. And it will be seen if, for example, the avionics or other loads are supplied by the 28 volt DC bus bar or directly by the power center. Okay, so I hope this has clarified a little bit the concepts I was dropping in terms of electrical architecture, generation, and distribution. Regarding the loads, there. Okay, sorry. Regarding the loads. This is one of the objectives. This is making most of the loads electrically, or at least being able to be supplied by electrical means. So, as I was saying, bleed generation now is performed electrically because air conditioning is always needed in the aircraft, but we are supplying it electrically by electrical packs. Anti-ice operation now is purely electrical. Taxi, this is the operation that the aircraft makes when it's at the gate until taking off. This is the road driving it's doing. Currently it's doing by the engine propulsion, and we are passing it to electrical, to an electrical taxi. This is with the engines completely off. For the emergency power supply, as I was saying, we've got a heavy and not very performant system, let's say. It's performant because it works, but it's not really optimized in terms of mass. And we are thinking on trying to get a hybrid electrical system. And when I'm saying hybrid, it's not because it will be electrical and something else, but hybrid because it will be by an electrical turbine plus, for example, batteries. A concept that I have already mentioned is also the electrical reversible loads that will be allowed. For the braking system, currently it's hydraulic with electrical backup, and we will switch to pure electrical braking system. And finally, related to the system, the landing gear will also be purely electrical. So this is what we want, and just as last chart, let's see what are we working on. Let's say that the good news is that we are finding that technology is available for most of the things we want to do. Okay, so here you've got some real examples of developments that are being done for this more electrical aircraft approach. Electrical wing ice protection is being developed pure electrical as pure electrical system. Flight control actuators are also becoming electrical. Full electrical APU is being developed. More electrical engine. This could mean a generator integrated in the engine. Is not a reality today. We are walking through that concept. Electrical air conditioning system, electrical pack, is a reality. Optimized cool system, as I was saying, air-cooled, liquid-cooled, to be decided, but it's in development and it's being demonstrated that it's a clear advantage to the systems we have today. And finally, electrical landing gear and electrical braking is also a reality. So even if the maturity is low, we have already some prototypes that are encouraging us to follow this path. So, and just to finish, what are the challenges we have with the more electrical aircraft trend? First of all, technological maturity. Currently, it's difficult to be a competitor with a very consolidated system, very mature systems that have been evolved for 50 years while we are trying to make these things evolve in less than 10 years. So this is one of our main challenges. This is be able to demonstrate that they can be real competitors. What do we mean by real competitors? We can make things exist, but also with good figures in terms of weight, in terms of cost, and reliability. For example, one of the elements we have mentioned was the TRU. This is the 230 28 volt AC-DC converter. This converter has been always non-regulated, and one of the reasons is the fact of no one has been able to demonstrate that the control topology can be better in terms of reliability. So in terms of aircraft architecture, we are ready to assume all the problems that a non-controlled device can translate to our network. Okay? So this is why reliability is one of our key points. We cannot decrease our reliability figures, because finally that would bring to an aircraft that could be very electrical but wouldn't fly, because authorities wouldn't let us. And finally, not to forget, the main objective is also to consolidate the advantages. We are not going through a more electrical aircraft because it's nicer or it's the fashion topic, but because it has real advantages. In terms of maintenance, we have a huge advantage. You can think on electrical wiring or hydraulic network. You will see. Aircraft dispatchability, we thought this concept of modularity, changing modules is more easy, faster, and you don't need a customization of the, let's say, of the spares as we have today. And finally, and last but not least, fuel saving. This is more electrical aircraft is supposed to bring important fuel savings. So let's try to consolidate that. So thanks.
One very short question. I have.
Well, I have a very general question. You mentioned in the new approach, in this new architecture, particularly in the DC buses, you design a modular and reconfigurable modules, and this is fine, but at the same time you say something that all these modules will be concentrated somewhere, and then the wires will go to the different loads, all the plane around. And clearly, the effect of the parasitics and the effect of the wires is very important and can ruin the DC buses. Is that? May you comment on that?
Okay, let's say that one of the approaches is also trying to solve is if it's better to have power distributed centers. I mean, by all the aircraft, or one only power center. Okay, so that's one of the points that is being solved. Anyway, what we are trying is that having for the low voltage DC consumers, they are most of them in the avionics bay and in the cockpit. So usually this power center has historically been close to that, so that we can avoid that kind of problems. Regarding the HVDC, we are assuming that that can be a problem. But let's say that with the electrical installation supposition we have made, and it's linked with the physical integration approach I was mentioning also, it's supposed to be overcome. It shouldn't be a problem. But I understand your point. I mean, this is one of the key problems of having an only.
How pulsating are the loads, and how the wires are affecting to the operation of the loads, and that's something.
That's it. Yeah.
Considering this approach. Okay.
Thank you. Thanks.
Okay. Thank you very much.